I'm going to talk about standard reduction potentials. So standard means this will give us a quantitative reference. You can find these potentials on a table of values. Reduction means it's the reduction reaction, so the half reaction as it's written will give you the potential, the voltage, for the reduction reaction. And sometimes you may need to flip that equation to get the voltage for the oxidation reaction. The standard cell potential is the maximum voltage of a cell under standard conditions. This is calculated using the reduction against a hydrogen standard cell. Hydrogen standard cell, or the SHE, the Standard Hydrogen Electrode. All reductions in the hydrogen half cell are measured at SATP. The half cell is assigned an arbitrary electrical potential of 0 volts. The hydrogen gas is at 1 atmosphere, and the solution is a 1 molar solution of hydrogen ions. Given this reaction, where the reduction potential of the ions becoming a gas is 0 volts. You then measure the cell potential against the hydrogen half cell by taking any other half cell and seeing what the voltage may be. We're going to do a couple examples and I'll talk that through. The equation that you can use for the standard cell potential, or the delta E naught, is the energy at the reduction potential at the cathode minus the reduction potential at the anode. Notice that in this reaction we're looking at both the reduction reactions. You are going to have oxidation occurring at the anode, so you usually will be given the oxidation reaction and you have to flip it to see what the reduction is. You could rewrite this equation being the standard cell potential is the oxidation plus the reduction reactions that are occurring. You then just have to make sure that when you're looking at your table of standard reduction potentials that you take the opposite sign and add it. The only thing that changes in those two equations are the negative sign. I like this one better because you're just taking the values from your standard reduction potential table and subtracting the anode from the cathode. So once you've chosen this reference cell, you could match it up with any other cell, and the voltage that is read is the standard reduction potential of that element. Here you have the cell notation for copper 2+ under standard conditions, and the measured potential is 0.34 volts. So this would mean it's a positive voltage and the reaction is occurring in that direction so that it would be spontaneous, and the copper 2 couple gets the standard reduction potential of 0.340 volts. Looking at another example, here's the zinc 2+ and zinc couple, and the measured cell potential is negative 0.7626. So this means that the thing you're looking at, the half cell, is actually being oxidized and the reaction's occurring spontaneously in the opposite direction. So the convention accounts that always write it as the reduction reaction, as I stated, which would be negative 0.7626. But in this reaction, the zinc would be oxidized spontaneously. That's why it's a negative standard reduction potential. Here's a short version of the table that is attached to this lesson. You can see that you have a bunch of positive and a bunch of negative half reactions here, and the hydrogen half reaction is 0 as your reference. Using these tables, if you don't have hydrogen as one of your half reactions, you can select one for reduction. So here we have the gold plus ion at positive 1.69, and select another half reaction to be your oxidation, and it's plus 0.34 for that copper half reaction. Take those two values, make sure that you balance your overall equation. You need 2 gold ions creating 2 moles of your solid gold to make sure that this is balanced. You then do your reduction, or your cathode minus your anode. So it's the positive 1.69 because reduction occurs at the cathode, minus 0.34. That 0.34 is the reduction potential at the anode. You do not change the sign here because this is given as the reduction, and we use the equation where it was reduction at cathode minus reduction at anode. This means the overall cell potential for this reaction is positive 1.35 volts. So when you're adding half reactions, the equation will be multiplied to balance the other half reactions like we did in the last equation. But notice we did not multiply the reduction potentials. These are not the same as multiplying a coefficient. You still balance the equation, but the potential is not multiplied. The oxidative strength is something that we can also get information from these tables. So most of the time, your standard reduction potential tables will have the most positive to the most negative and listed in that order. Something higher in the table on the left will mean that it's more likely to react in a reducing manner, inducing oxidation. Thus, it is an oxidizing agent or oxidant. Here you can look at the relative strength and say something like the fluorine gas is a stronger oxidant than the silver ion because it's higher up in this table, fluorine being here and silver being here. Or you could say the copper ion is a weaker oxidant than the cerium ion because it is lower in this table. Reductive strength is just the opposite and works exactly the same way, except now you're looking at substances on the right hand or the product side, and you're saying that those lower in the table will have a greater tendency to be oxidized. So the silver is a stronger reductant than gold because silver here is lower on the product side than gold is in this table. So oxidative strength and reductive strength are opposites of one another, and this table of values, because it's usually from most positive potential to most negative potential, can tell you the strength of those half reactions. And thus, if you take two of the half reactions and add them together, put them in the equation where you do the cathode minus the anode, or flip one based on its reductive or oxidative strength and add them together, you can see which direction the cell paired with those two half reactions would go. And then you can see the spontaneous direction of that reaction.